Hello? Hello?
It doesn't help us.
Oh, okay. All right. All right. Okay, so so in this case, we found that this, say on the left side where interaction is weak, okay, if you reduce the temperature, you see the conventional normal gas to superfluid transition. But now, if you make the interaction stronger, then there's actually a quantum phase transition driven by quantum fluctuation into another phase, which is the insulating phase. Okay? And near the critical point, okay, you can see all the energy scale either drop to 0 or some other length scale for its correlation length is expected to diverge. Okay? So the microscopic physics actually doesn't play an important role anymore. So we expect to have universal behavior in the critical regime. And this here, the only thing that only the energy scale you can find will be the temperature, and only length scale would be, say, de Broglie wavelengths. There also, so therefore, there's a lot of interest trying to figure out whether they can see the universal behavior, and the behavior can also be connected to other universal behavior in other physics. Okay, and we'll further talk about some equilibrium study. Okay, look at the universal thermodynamics, and then go into dynamics. Okay, all right. And we'll approach it to talk about how we approach the critical point from different directions. Okay, all right. And ultimately, there's, as I mentioned, there's been predicted, particularly for Bose gas in 2D, okay, expected there's a certain kind of conformal symmetry, that's symmetry between space and time. And then you can apply the conjecture, so-called gauge gravity duality, and then you can, if you look at dynamics, you can potentially really confirm this kind of a holographic idea, provided by this diagram. Should be such that draw this diagram to show that if you look at the quantum particles on d dimension, this d-dimensional surface, okay, in principle, if they have this kind of symmetry, conformal symmetry, okay, then it can be mapped to physics in higher dimension. Okay, in this higher dimension, d+1 dimension, all the particles are connected by strings. Okay, and this idea first came about from this Hermann-Sinner, okay, many years ago, and Subir identified that this Bose gas and 2D lattice would be a good candidate to study the duality. Okay, so my outline. First, I talk about our system, our experiment approach, okay, to this Bose gas in lattice or the 2D Bose gas. And then I tell you about some equilibrium measurements. Okay, so, and in particular, this how do we approach a critical point, and we can see the scale invariant criticality. And then there's an important issue that to address. How can you even look at this critical behavior when you have particle in the trap? You have homogeneity, you have all the other length scale that in principle can play a role. And what will be our solution to address that? And toward the end, I'll be talking about this our more recent experiment on non-equilibrium dynamics. I will look into two limits. One, you do a very fast quench, fast and on time scales that we call quantum quench, and see the Sakharov acoustic oscillations. And the other limit, try to do everything very slowly, okay, like intrinsic dynamics that Lauren talked about. And what happens if a system evolving very, very slowly? Hopefully, we can use a transport or linear response theory to describe the system. I'll tell you our approach. All right, so this is our experiment. Okay, this is cesium atoms. Okay, and we can condense them, can load them into 2D gas. And to get them into 2D gas, what we do is that we provide a strong confinement using these two blue lasers. Provide a strong confinement in the z direction. How strong? We need to make it. We want to make it so strong such that all the relevant energy scale, like kT, a chemical potential, they're all very small compared to the excitation energy in z direction. So in the z direction, they are compressed to only single quantum state. Okay, no matter what happens in the radial direction. In the radial direction, then the system almost classical because our radial confining frequency is more than factor 10 lower than the many body energy scale. Okay, and on the horizontal plane, XY plane, we can turn on the beams to form the lattice. Okay, or if you turn off the lattice, then you get a 2D, two-dimensional gas. And to look at the system, these are almost like single layer, this only mono layer of atoms. And then you illuminate this sample with a beam in the z direction. Okay, and then you can look at the system from the top. To characterize this kind of 2D gas, this Dima-Petrov geometrical, they provide this the connection, the behavior of this two-dimensional gas in the so-called quasi-2D regime can be connected to the real 2D physics using this relation, can relate them to the coupling constant, which is dimensionless number, okay, and the 2D scattering length in the real 2D world. And then that also connect to the 3D scattering length that we control using phase bar resonance and so on. So in our experiment, we'll use a 3D scattering length to calculate G, okay, the coupling constant, dimensionless, and this is A3D, the 3D scattering length, and then LZ is oscillator length in the Z direction, okay, and then we can compare to 2D physics using the first equality. All right, so here's the animation, okay. And there are many other groups also have the capability to do in situ imaging now. All right, so this is a typical image we have of looking at about 20 to 40,000 atoms in this two-dimensional trap, okay? And with the following pixel size resolution. And we look carefully into this, the distribution. You can also see fluctuations, okay? And these fluctuations shows that if you look at the fluctuation at the wind, then you can see the fluctuation it confirms it's a kind of thermal gas nature when density is very, very low. Okay, but near the center, then we really see interaction plays an important role. Okay, when you use the phase bar resonance, many interaction larger and larger. Now we see there's a different correlation length and different amplitude. Okay, that can be understood as the interaction suppress, okay, the density fluctuation. It costs energy to populate those excited states. Okay. Another way to characterize it by looking at the so-called this structural factor. You're pretty much looking at the density fluctuation at certain length scale. Okay, and once and you can find this expression Landau-Lipschitz in the equilibrium system. It can related by this dispersion, how much energy you need in order to populate a certain momentum, certain energy, and then this is this hypercotangent is just a sum of a quantum fluctuation plus a thermal fluctuation. And then we can explore the two regimes. If you make the interaction weak, say G is small, okay? In that case, temperature can be stronger than this interaction scale. In that case, this is what we see. We see a fluctuation that's higher than this Shot noise. Okay, and Shot noise is 1. Okay, that's confirmed with a thermal gas. This is Shot noise. But when interaction is strong, then you can see the fluctuation being suppressed the other way. Okay, is now we're seeing that this sub-Shot noise fluctuation. When you go to higher momentum, everything converges to 1. That's because when you go to small length scale, then all you're seeing is the single particle effect. All right, so let me postpone this correlation. It's very interesting. I'll come back to this later. But first, tell you about what we do to understand the density profile. Okay. All right. And our approach has been so far using the so-called local density approximation. We see higher density here, and we can assign a higher chemical potential. Okay. And that corresponds to a higher chemical potential at the center. When you see a lower density in the wind, okay, that corresponds to lower chemical potential. And actually, when the chemical potential is low, large, and negative, okay, then we found this the density tail, okay, can be well captured by this mean field formula. To zeroth order, it's just this is an ideal gas, and then plus a mean field. Okay, from here, from the density tail, we can determine both chemical potential as well as temperature. So for equilibrium system, that's how we determine these two parameters, and then we can just, we know there's certain symmetry, cylindrical symmetry in our system. We can convert the density profile into the equational state by eliminating the dependence on R. Okay, so we see how density depends on chemical potential and also the temperature that we determine from the wind. So from the equational state, okay, that tells a lot of information. And more recently, we can get pretty high quality by determining the equational state, as in I'm not sure it's as good as Martin's, but at least it's sufficient for us to determine all the other relevant thermodynamic quantities. Once you know equation state, and turns out the system scale invariant just like unitary Fermi gas, you can determine other thermodynamic quantities. All right, in 2D gas, turns out as long as the coupling constant is a scalar, okay, then you expect the scale invariance to work, and we have some earlier experiment to verify that. But here we try to go beyond that limit, try to make the interaction stronger, and there is no very good theory anymore. But we can still perform measurement, and what we did is that we load the atom, okay, into the 2D gas. We can use a phase bar resonance to make the interaction stronger, and we can cover this range about a factor 10. And then we can also load this 2D gas into the lattice, still in the superfluid regime. It's a weak lattice, so never approach a Mach insulator. And then we can change the interaction, use the phase bar resonance to scan the scatterness. And then we can cover this range from 0.44 all the way to about 2.5 or something. Okay, so this figure kind of summarizes the phase diagram. Once your density high enough, chemical potential large enough, you start to see this the superfluid regime. Okay, and later I'll tell you how we determine the phase transition point. Okay, and so I'd like to mention we are certainly not the first group looking into the equational state. Okay, and we are not but we're trying to understand whether there's when you go to a strong coupling regime, maybe there's some new physics, including some prediction there could be some kind of crystallization when G is as large as 10. Okay, but so far we can only go to about 3. Okay, but what motivated us to do this is that there are a lot of kind of logarithmic corrections in 2D gas. Okay, and 2D gas itself is very strange. Okay, first of all, if there's no interaction, you got kind of a true 2D gas on the plane. If there's no interaction, turns out the system does not even condense. Okay, and with finite interaction, and this formula been derived with a coefficient determined by Nikolai and Pokoyev and Boris Vitunov, this 380. So you can see this crazy double log behavior dependence on the 2D scatterness. You can just think about the limit. When scattering goes to 0, log will diverge. Okay, then double log will also diverge, but it's diverged really, really slowly. Right? Okay, so interaction plays an important role. And if you look into the, say, what we can more easily measure this the ground state energy. Okay, there's a whole bunch of calculations in the past 40 years. Okay, the reason there are so many calculations, calculation is really, really difficult in terms of expansion, in terms of this log and double log. Okay, even somewhere you have triple log and so on. And you can see, starting from the mean field, people determined mean field 40 years ago, immediately provided first beyond mean field calculation. And then there's so many calculations because every time people try to go one order more, and then turns out later there are some corrections showing that your calculation is wrong. Okay, so it's a different coefficient and so on. Even people coming back to mean field, double check, we are really on the right track. Okay, even more recently, you can see the numbers start to converge. Okay, well, except for the last one. Okay, and there are so a lot of arguments how to whether this perturbation approach really allow you to really get good predictions. And most recently, a few months ago, when I talked to both what's his first name, Sakharov, and also Ivan Kostin, they are still arguing the last the correction in the third order. There's no agreement. Okay, all right.
I can tell you who's right.
Yeah.
I can tell you who is right.
Ivan Kostin, pretty sure he's right. Okay, but yeah, well, they are both pretty sure. Okay. What? All right. Okay. So, we do the experiment, and so what we do is that if you go into the superfluid regime, we can determine the many body coupling constant just by d mu dn. Remember, in Thomas Fermi limit that you have mu equal to gn. Therefore, d mu dn equal to g. So mean field theory give you 1. Okay, this is y equal to x. However, when you make the coupling stronger and stronger, we start to see a deviation. I'm using 2 symbols. All the solid dots are measurement in the 2D gas, without the lattice. Okay, and you say, well, it looks like there's some deviation. That we try pretty hard. This is the best we can find. Okay, and when you also load the 2D gas into the lattice, still in the superfluid regime. Now we can further make the interaction stronger. Okay? And then here you start to see there's a really significant deviation from the perturbation, also mean field. Okay? And it looks like this another calculation by Tobias Starchev and Eugene Daimler based on the renormalization against the Landau approach provide a better prediction. However, when I talked to both of them, they said their calculation in principle cannot be extended beyond G equal to 0.5. Okay, so this could be coincidental. All right, to really determine the phase transition, the BKT transition is very, very small. I show you this equation of state. It said no any interesting feature to find it. So far, the most successful way for us to identify the critical point is by overlapping the equation of state, okay, and see whether they follow this kind of the predicted critical scaling law. Okay, that is when density deviates a little bit from critical density, then the difference should be a function of the deviation of chemical potential from the critical value normalized to the coupling constant. Okay, and this seems to be quite successful for us to determine the critical values. And here I summarize, okay, the phase diagram as a function of interaction strength. Okay, now here is the critical chemical potential we need in order to drive the system into superfluid as function of G. Okay, and you can see also the lower panel is a critical phase space density we need in order to see the superfluid transition. And this is the one that you see that this is a double log correction, okay, or a single log correction in terms of G. Okay, eventually it's a diverge. Okay, and but this is the best we can do within this range. Yes.
In this graph, how do you know that the system is superfluid?
Oh, that we're using this. Okay, we can overlap. Yeah. So when okay. All right, and also compared to two calculation classical field renormalization calculations, and well, we don't have very good, difficult to distinguish. Okay, but the point is not to distinguish them because both theory are not supposed to work beyond 0.4, 0.5, and so on. Okay, so finally I'd like to come to quantum criticality. Okay, but I'd like to stress that this interaction actually considered already pretty strong from this Nikolai's earlier calculation. He considered this superfluid helium film is around 1.8 or something around here. Okay, and we can now kind of cover this regime going all the way almost to 3, but there are also other predictions go to 10. You can see crystallization and so on. So around here, okay, we also look into the quantum critical behavior. What we do is that now I'm plotting this the two phases. Okay, now this one side you have the normal gas at finite temperature, zero temperature become vacuum. You look at the vacuum to superfluid transition. Okay, this in the lattice, and then we can identify this the TC. Okay, the TC eventually drops to 0 when density becomes very, very weak. The system described by this Bose gas, okay, dilute Bose gas universality. Okay, and the low enough temperature you can see this linear dependence. Okay, high enough temperature we start to see this some finite temperature correction. So finite temperature is here. Okay, all right. And in this critical regime, we can also double check and show that with the equation of state, does follow this kind of critical scaling law with the critical exponents. Okay, that Z is dynamic critical exponent, nu is a correlation exponent. So let me say a few more words about this. So this equation of state as a function of this chemical potential. When you in the lattice, the way I understand now that is, you see the scale invariance is because when temperature is small compared to the bandwidth, you are only looking at the dispersion, the very bottom of the dispersion. Very bottom of the dispersion quadratic. Okay, so therefore there's no scale. Okay. But when temperature is high enough, you see a deviation from scale invariance. That's because the ground state bandwidth becomes important. Okay, you start to see there's a new length scale, new energy scale comes in. Okay, therefore the scale invariance broken down. Okay, so and also like to mention this kind of system. This phenomena also been seen already in condensed matter several years ago. Okay, it's the same kind of phenomena Like when you see a linear increase of critical temperature, eventually it bends over, okay, in a similar way. And in this case, this is a Fermionic system. You need to apply strong enough magnetic field to imbalance the chemical potential for spin-out, spin-down electrons. And then the majority electrons has a chance to pair and also form this BEC. So therefore, this is equivalent to a 2D BEC, this 2D superfluid quantum phase transition we studied. All right, so let's address the fundamental issue: how can we ever really see quantum criticality in the trap system? The main problem is, like when you get closer and closer to critical point, what happens is that the critical region gets smaller and smaller. When the critical region gets smaller, okay, only a small amount of atoms are really in the critical region. At the same time, the quantum criticality suggests correlation lengths will diverge. Okay, correlation length will diverge. Okay, so eventually, when you approach zero in the trap system, something must break down because critical range is small and correlation length is supposed to diverge. Okay, and in our if you plug in the number, in our case, our critical range is still about 5 or 6 micron. Okay, and our correlation length, thanks to cesium very heavy. Even go to 5 nanokelvin, our correlation length is on the order of about 2 micron. So we're only about a factor of 2.5 or 3, okay, below the size of this critical ring. Okay. To further go into really check this conformal symmetry and so on, gauge gravity duality, turns out we really need to go to the tip of the Mach lobe. There, the order energy scale is another factor of something, 4 or 5 or something lower. If you want to really see those kind of critical phenomena, we need to go to much lower temperature. Critical region gets smaller, and based on this kind of trap geometry, actually it's obvious we won't be able to see those kind of criticality. Okay. So our approach is the following: we really need to throw the harmonic trap away. We are really approaching the limit. Okay. So this criterion, critical regime or the width of the ring should be larger than de Broglie wavelength, and everything should be larger than the lattice constant. So this is our preliminary result. So we're trying to abandon our harmonic potential and using this box potential. Okay, and what we try to do in the beginning, the harmonic trap, and then provide this the box potential to push all the high entropy sample, high entropy particle away from the center. Okay, and then put another beam to balance the curvature at the center. Okay, and eventually this box I just drew with my PowerPoint. Okay, just and then rotate with the angle and show that this indeed is a good box. All right, and the whole point is that now we like all the atoms to be in the critical regime. If we can control the chemical potential temperature properly, that all the particles can contribute, and it is a large size. Okay, to see the correlation length, I think it shares similar idea as Zoran. Of course, we don't really have to go to square. We can also go to some other dimension, some other geometry. Okay, but we know this might also work, but this will not work. Okay. Right. So toward the end, I'll tell you how we prepare this finite shape potential. But now, at the moment, we're trying to make the box as flat as possible. It's very sensitive to any small tilt. Okay, we're 2D gas, so we worry less about gravity because it's perpendicular to the gravity. But any magnetic field gradient, anything can push a particle one way or the other. And the other things, how do we determine the chemical potential temperature, okay, and so on. We're now working on those issues. All right, so let me now move to the next topic, trying to understand the non-equilibrium system. There are many fundamental issues regarding non-equilibrium physics in core atoms. I'm not going to just discuss them. Any topic can take forever. Okay, but essentially we are working on this pretty well isolated system where we expect energy particle number to conserve. Okay, and there are this and whether you can describe the system with the transport equation. Okay, whether the system can really thermalize, there are many issues. So our experimental approach is trying to identify whether they are universal phenomena, universal scaling, universal behavior that we can identify. Okay, and at the moment we're trying to go into two limits. One is trying to do everything really fast, they are quenched. fast compared to all microscopic time scales. Okay, that we call quantum quench. If it controls certain parameter, then microscopic time scales. The advantage here is that we can use kind of what we learned about quantum mechanics. We can do a projection. Okay, but you need to make sure it's diabatic. Second, try to do everything very, very slowly. Okay, and make sure there's some kind of local equilibrium so we can apply the transport equation. In that limit, okay, what we call transport, we'd like to see whether we will be able to determine, say, conductivity, thermal conductivity, and so on. I'll show you these two experiments. First on quantum quench, and then on quantum transport. All right, but before we can do this, I'd like to address on the different time scales in the co-atom experiment. It's not as obvious as in condensed matter that we indeed have all the regimes, okay, to study, for example, transport, because we know this is a new concept, whether we can assign chemical potential temperature to each pixel, all right, to each small part of the sample. So what we did is the following. We first just do a small quench, and then see the dynamic. This is not in linear scale. This is 13880 millisecond. Okay. If you look at the density distribution, if it is a kind of a radial distribution, high density at the center, low density in the wind, then you can see it takes a long time for the system to evolve. Okay, from 0, and this is a log scale, 1 millisecond, 10 milliseconds, 100 milliseconds, and so on. Okay, if you only look at the density, it looks like it takes a long time to evolve. Okay, that's typical for co-atoms. But if you can look at the fluctuation, you can see fluctuation evolve in a much shorter time scale because this is a local property. It doesn't really need the propagation all the way to the wind of the sample, okay, to establish a global equilibrium. So in this experiment, it does suggest there are different time scales for global equilibrium and local equilibrium. But here, if you look at this, it couldn't really make too much out of this. We tried to analyze, now couldn't. Later we realized we really need to use a more advanced technique to understand the evolution at short time. That is, we look at the structural factor, look at correlation. So the same experiment now, if you just analyze the correlation at different length scale and time scale, this is what we found. Okay, we found that for a shorter length scale, it turns out after quench we see these oscillations. Okay, the oscillation like this. And the longer length scale, the oscillation is much slower. Okay, and they are actually related by the sound speed. Okay, the length scale and time scale are related. And if you do the experiment in the superfluid, then you can guess the ratio will be just the sound speed. Okay, and we developed some theory model trying to understand. Remember, when this curve goes up, okay, KT is larger than interaction, then this you have this more in the classical regime. Okay, and once you do the quench, okay, then it turns out you can see the oscillation because different wavelengths they are interfering at different time with different length scale and time scale and so on. And somehow when you talk to the right people, then go to the different people and get different ideas. Okay, then we turn to talk to my colleague, okay, working on this cosmology. I say what you are seeing is very similar to this the oscillation you see in the early universe and not revealed from the cosmic microwave background. Okay, this density, temperature, this speckle and so on. And that's because in the early human evolution, the system also hydrodynamics. The only kind of thing that relate the fluctuation, different length scale, time scale, is the sound speed. Okay. Therefore, we got the idea. Then in our case, we can also do similar things. So we try to prepare the sample also in the similar kind of initial condition as early universe. That's white noise. Okay, starting with the white noise. And do the quench in the proper direction and then see the enhancement of the correlation. But since we make it larger, so we are more in the classical regime. Okay, quantum regime will go the other way. Okay, and then compare this with this CMB. All right, as I can a few more minutes, I'll finish the last part, trying to talk about transport. All right, the transport, we are doing very, very slowly. And our the idea is whether we can really assume any thermodynamic quantities at every position and time. Okay, and we think we can do that. We can do this tomography. Okay, and once you determine these thermodynamic quantities, a function of position and time, first put it into a continuity equation, determine the flux. okay? And this is source, this is a flux. Okay, this is any extensive variables. And once determine the flux, you put it into the second equation, transport equation, and hopefully you can determine this so-called kinetic coefficient, trying to relate the flux to the thermodynamic force. Okay, so I quickly show you the current problem. We haven't really finished the whole thing, but what we do is that we prepare the sample and try to induce a very, very slow dynamics intrinsically using this three-body loss. We made a scattering length 500 Bohr, not too big, it's not too small, and then see the loss in the time scale about about 700 milliseconds. About 500 Bohr, right? Okay, so need to wait for about 700 milliseconds. So once we know, and we know the equation state pretty well, okay, and then we can determine all the energy profile, entropy profile, and so on. Once you know all the profile, like I said, you can put it into the continuity equation, determine the flux, particle flux, energy flux, entropy flux. Okay. In this kind of system, only 2 degrees of freedom, so focus on the first two. Okay. Density conservation, energy conservation provide us the fluxes. Okay, and this is the result. Okay, so it looks like this is a very interesting behavior if you look at the particle flux. Okay, somehow if we lose particle, these are three-body laws, lose particle at the center. Now there's a positive flow, the particle flow toward the center to replenish the whole. But at the same time, you also have a particle also flowing outside. Okay, that turns out to be coming from this thermoelectric effect because there's heating associated with the particle loss. Then the heating also push the particle go in the opposite direction. Okay, and that corresponds to this thermoelectric current, and this the center part is try to fill the hole at the center. Okay, but if we look at the energy flux, it turns out there's no this kind of behavior, and these two effects canceling each other provide us a very good hint how to really decompose the flux into the gradient of the corresponding thermodynamic forces. But energy and particle, these are the two kind of thermodynamic conjugate variables, mu over t, 1 over t. So we have some, we can determine hopefully these 4 coefficients. All right, last slide. If we can determine all 4 the 4 elements, what can we do? Okay, with this 0, 0, 0, 1. Okay, first of all, there are global properties. We can check the time reversal symmetry. The Onsager assume microscopically transport is still time reversal. Okay, symmetric. So therefore, this should be transposed. This should be symmetric matrix. Second, there's also from second-order thermodynamics or even additional assumption that the so-called maximum entropy ascent. Okay, so this entropy should increase as fast as it can. Okay, within the configuration space, and that lead to the determinant of this matrix should be larger than 0. Okay, and also the diagonal part should be larger than 0. Okay. Second, also local properties, and so trying to work out this method. There could be some error that, okay. Once you determine kinetic coefficient, they can be related to the conductivity, thermal conductivity, Peltier coefficient, and Seebeck coefficient by this complicated this equation. I think there is some work we can do. We can reverse it and determine all the coefficients. All right, that to summarize. So 2D gas and in quantum criticality, we're now moving toward this conformal symmetry that to get space-time behavior, and quantum quench transport. Okay, at the moment working on the kinetic coefficients, and in the future we'd like to do experiment in the box potential. Okay, and if you are interested in the technical setup of the box potential is shown here. And finally, I understand my group member work on this on the 2 experiments, 2D Bose gas as well as this lithium cesium Bose Fermi mixture, which we just recently got boson and condensed and found the phase bar resonances. Thank you.
Yeah, thank you very much. It's time for questions.
Go back.
So I'm just wondering if there's, I mean, would you determine the critical point for strongly interacting both gas by rescaling the measurement? Is there any other signature of the transition aside from that? Any way of doing that?
Yeah. Other group had tried that in Dolan experiment, and it's really look at the superfluid. Okay, in our experiment, we're not repeating those experiments. We just look at the scaling behavior. Okay, and then you can find this scaling only near the critical regime, okay, but not in the superfluid, certainly not in 3D as well. Okay.
Maybe following up on it, how do you know it's actually a quantum critical point and not a quantum critical region, for example? Do you have access?
We have no access to quantum critical point. Right? We can only look at the finite temperature behavior. All we can say is that when the temperature low enough, we start to see the scaling, okay, and from the exponent we determine, okay, they agree with the theory, okay. So it's likely when we go to even lower temperature, maybe something new will happen.
Following up, speaking of temperature, I thought
Yes.
you were going up to 8 T or something like that?
Mm-hmm. Right.
And the bandwidth is like
80.
4.
No, bandwidth in 2D is 80.
Bandwidth is 8.
Okay.
I have another question.
Yes.
For this determinant of sigma being positive,
Yes,
exact
yes,
thermodynamics.
yes.
It sounds nice, but like, is it the case where sort of, if you mess up the experiment, not because you're bad, because you all mess up experiments,
Yeah, sure.
that will also automatically drive it to positive value?
Possibly.
You
So,
see what I mean? Like, yeah,
so it's,
yeah, your entropy will grow because, you know.
to me, there's a lot of question whether we really believe in theory, whether this is there's a maximum entropy, this entropy of second law thermodynamic, whether it really apply to our system. Okay. Probably over long enough time, yes. In short time, I'm not sure. Okay. So this at the moment we're just trying to determine the matrix, these 4 coefficients, assuming we know nothing about anything. That try to determine them independently. Okay. And then try to evaluate determinant, try to see whether it's symmetric and so on. Okay.
Yeah, just consider sort of what artifact is susceptible to, right?
Right. Okay.
The
That's
perfect experiment will automatically drive it to positive, or
yeah, true, possible. Yeah, I cannot answer at the moment. Okay.
Another question that also came up in Zolan's one. So
Yes.
you both have sort of this box potential.
Mm-hmm.
And I mean, strictly speaking, you still have the hard wall.
Yes.
coming in, right? So you still have a lot of curvature as you go very
Mhm.
close.
Yes.
So are you basically saying that mostly you do it to have the flatter profile and you could do it in harmonic flat if you have sufficiently many particles?
You cannot do it.
Or is it a true advantage?
no, it's different density of space. Different density of space.
Right. It is.
From doing harmonic and going to thermodynamic, take
But
harmonic.
you don't have periodic boundary conditions. This is what I'm getting at. So it's not sort of the uniform system in the sense of having periodic boundary conditions.
I would say that one periodic boundary system is not a real uniform system. Theoretical convenience.
So from our point of view is that we just we are not trying to. If you try to go have a correlation length larger than the size of the box, it's certainly going to fail.
Sure.
Right. So when
It's a bit that size, yeah.
right. So I'm trying to explore the regime going beyond the regular oscillator length all the way to the box the box size, and with this 20-30 micron size box, I think we can go to about few picokelvin. That's a pretty large range for to explore. Okay. Yeah. And what in the experiment we're just going to cut all the edge just look at the center part when density is uniform.
And for some, the way I would put it is for some studies, the gain is basically like increasing from oscillator length to cloud size. So say we have like a 50 microns or whatever, okay? Uniform, compared to something that is harmonic but also extends over 50 microns. But if you want to study something like the power law decay of correlation functions in the 2D gas, right? Then you start revolving it, with some non-homogeneity already on a micron, because that's your oscillator length. So it's not, you will be able to see something over 50, but just quantitatively it's not going to be right? Because it's continuously changing, right?
Well, let's thank Cheng Chin again.
All right. Thank you.